Okay, let me pick this back up now from where I left off, since I had to sign off and go to a Zoom meeting. So you guys know how that is. So we have a wire with current coming out at us. We would like to know what the magnetic field is a distance r away. If we use Ampere's law, which states that around any closed loop, the magnetic field dotted with some small line element is going to be equal to mu naught times the current enclosed by that loop. Okay, so we, just like in Gauss's law, we imagine that we have a closed loop. Remember, this was called an Amperian loop. Okay, it's a closed loop, distance r away. And we looked at, I think we looked at the dot product here. Actually, we looked at a number of things, right? So the magnetic field from the right-hand rule at points along that Amperian loop are going to be tangent. We're going to be tangent to that loop. So I'll just draw in a couple of these. All right, so there's the magnetic field. We're going to have small DS's, right, along that path. And so if we were to look at this dot product, then B dotted with ds, it's going to be the magnitude of B, the magnitude of ds times the cosine of the smallest angle between those two. And so theta now is equal to 0 degrees, cosine of 0 is 1. So that dot product in the integrand then just becomes B ds. So Ampere's law then looks like this. This is integral around the closed loop. So it's going to be B ds is equal to mu naught times I enclosed. B is a constant in magnitude as we go around this loop at radius r. So B comes out of the integrand. And so we have this equation. This now is just going to be the sum of all of the ds's around that closed loop. And so that's going to be nothing more than the circumference. So then this is going to be B. This would be 2 pi r is equal to mu naught I enclosed. Okay, and if we solve for B, B then is going to be mu naught I over 2 pi r. And that's exactly what we got earlier. Okay, so you can tell no serious integration here. We didn't have multiple lines of algebra, and with the symmetry here of a straight line current carrying wire, a circular Amperian loop around that wire enclosing that current, we can employ Ampere's law. So Ampere's law can be used in many cases where there is some symmetry. It can be used for the following current distribution. And so if we look now at what is called a solenoid, and I'm not going to do the derivation for you, I'm just going to explain this. So a solenoid is like a slinky, right? A slinky configuration. A slinky configuration with a current going through it. So you would imagine that it's, again, a helical configuration with current going in and coming out the other end in a continuous fashion. And so this is a helical configuration, right, which is called a solenoid. So one can use Ampere's law here, and if you're up to it, then you can look at section 29-4 for the details, and I'm not going to redo that here. But at the end of the day, what happens is that the magnetic field inside the solenoid, is homogeneous and constant, and its direction will be dependent on the direction of the current, and so again, you can look at some of the figures in your textbook. So given this configuration, the magnetic field is going to be in this direction. Okay, so will be the direction of the magnetic field inside that solenoid. So inside, it's constant and homogeneous. Outside, the magnetic field is zero, which is interesting. Now, there's some caveats here, right? So the solenoid must be relatively long, right? Relatively long, so that within the main body of the solenoid, right, the magnetic field is constant and homogeneous. At the ends, you would get fringing effects, much like a capacitor exhibits at the edges of the plates. So, but for the most part, if the solenoid is long, then the magnetic field inside is pretty constant. And the value of that field is going to be B, is going to be equal to B mu naught N times I, where you remember that mu naught is equal to 4 pi times 10 to the negative 7 Tesla meter per amp. I is the current, and N is what is called the loop density. And that is the number of loops per unit length. And sometimes you'll see this as the linear loop density, just so you know that it's a number of something per unit length. In this case, it's the number of loops per unit length. And so applications-wise, right? Applications-wise, so if you've ever taken an MRI, right? This is magnetic resonance imaging. So when you go down so if you were to imagine, this is a large cylindrical MRI instrument, and here you are. Whoops, let me get rid of that. So here you are in the MRI. And so around you, all right, around you is basically this, helical solenoid, right? So this is made out of superconducting material. Superconducting material. And it's actually being bathed in liquid helium. So inside here is liquid helium. And the liquid helium is at 4.2 Kelvin. 4.2 Kelvin, liquid helium-1 to be precise. And that temperature is low enough to keep the material in the superconducting state, and hence the magnetic fields can be very high. So the magnetic fields in magnitude here, right, could be 2 to 12 Tesla, depending on the kind of instrument. So very large magnetic fields inside MRIs. And so, again, some of the things that we've covered over the course of the semester, superconducting materials, magnetic fields, solenoids, right, all come into play in this medical application, right? So this is a medical application of several phenomena, right? Medical application. All right, very good. I'm going to end chapter 29 right here. We will omit the section on current carrying loops as far as magnetic dipole discussion is concerned. So we'll omit section 29-5. All right, very good, people. Stay tuned. Later.